This is Software Engineering Radio, the podcast for professional developers, on the web at se-radio.net. SE Radio brings you relevant and detailed discussions of software engineering topics at least once a month. SE Radio is brought to you by IEEE Software Magazine, online at computer.org/software. Are you a tech-savvy developer with an inquisitive mind? SE Radio has an opening for a new volunteer host to join the team and produce 5 episodes per year. Contact show host Robert Blumen at robert.blumen, that's BLUMEN, at gmail.com for details.
For Software Engineering Radio, this is Edaena Salinas. Today's episode is about machine learning with Katie Malone, who is a data scientist in the Research and Development Department at Civis Analytics. Katie has a PhD in physics from Stanford University, and her background is in particle physics. She worked on searching for new particles at CERN in Switzerland, which involves data science and machine learning. Katie is also an instructor of the Intro to Machine Learning online course from Udacity, which I personally really liked. And she's also host of Linear Digressions, a podcast that explores machine learning and data science through interesting and sometimes unusual applications. Katie Malone, welcome to Software Engineering Radio.
Well, thank you so much for having me. I'm delighted to be here.
Machine learning is widely used. We see it in search engines, speech recognition, language translation. Now we see it in our Netflix recommendations, and most recently in driverless cars. In the coming years, we are going to start seeing it being used in more fields. First, I want to begin by defining what machine learning is. What is machine learning?
So let me take a step back and answer it this way, which is that my background is in science, and so I have this kind of innate belief that there's truth in the world and that science is one of the ways that we can understand that truth, that we can get it out of the world around us. And it's really hard to measure truth directly, but one of the things that we can do instead is collect data on the world. And then if we analyze that data, then sometimes we can pull out the truth that way. So a true thing about the world might be something like, I'm interested in watching this movie, or it might be something like, there's a good way to translate this sentence that I just said from English to French. And the thing about machine learning is, in my view, a suite of tools that allows you to analyze that data and figure out, what's actually going on in the world and how that's expressed in the data. So usually it involves pretty heavy computational lifting. Obviously, machine learning is the machine component of it is implying computers. And then there's also usually a heavy dose of statistics and very often additional scientific fields as well. So if you're trying to study something like human behavior, then there's a whole suite of things that you should be aware of about the way that humans, behave in the world, and things like behavioral psychology and economics and sort of all those other things that give you context about how to study, the thing that you're interested in studying.
So what you're mentioning is machine learning can be about measuring the truth through collecting data and analyzing this data. How does this relate to the field of artificial intelligence?
Oh, that's an interesting question. I once heard a good description of artificial intelligence and the distinction between machine learning and artificial intelligence. I think it's a little bit of a false distinction, but the idea is that machine learning focuses more on understanding that truth, trying to understand what's going on in the world, or to measure what's going on, or to make predictions perhaps. And artificial intelligence is a little bit more thinking one step further. Once we have those predictions or we understand what's going on, how can we make better decisions, or we can change, the way that we do things in the future so as to take advantage of those insights that we've gained. So artificial intelligence sort of builds upon machine learning, and I feel like it is kind of adding that layer of decision making or changing the way that you do things as a result of machine learning.
Let's walk through a simple example of machine learning. One that I see all the time is in email clients like Gmail. When I get an email, there's a button to indicate if an email is spam. Let's talk about what can happen under the hood in a spam detection system. Once I indicate that an email is spam, I am telling the system, showing the system something. What can machine learning do with that information in order to start building a model about what spam is?
Yeah, sure. So email is a really good example of a case of what we would call probably supervised classification. So there's two parts of that. Let me break that apart. Supervised, the idea of supervision in machine learning is the idea that somehow you have the correct answer for some of the cases. So in this case, the correct answer is you manually labeling an email and telling it that it's spam. And kind of implicitly, if you don't tell it that it's spam, then it assumes that it's a legitimate email. And that may or may not be a correct assumption, but let's assume that most of the time, the labels, so to speak, of these emails then end up being reflective of what the emails actually are. And then classification is the idea of we're trying to sort things into two buckets. Is it spam or is it not spam? And so the idea of machine learning is that based on the attributes of the email, we can make predictions. We can learn what a spammy email looks like, and we can extrapolate those patterns onto new emails that we don't know whether they're spam or not, and we can make a good prediction. So in the case of something like what looks like a spammy email, it's probably going to look at the words in the email, potentially also the domain that the email is coming from, but especially for emails, spam has very particular patterns of like the words that they actually use in spam tend to be pretty distinctive. Like they're usually trying to sell you something. There's usually lots of superlative adjectives about how great it is, or maybe they're trying to get you to send money to somebody in some foreign country. Very often there's grammatical mistakes. So based on the presence of particular words, like Nigerian prince or whatever, then it can, from all these supervised cases that you've given it where you've said that this is spam, it can basically learn those patterns and then apply those patterns to new cases. And hopefully then at some point you don't have to manually label any more emails. It's just figured out what spam looks like.
So that we don't need another human in the loop to indicate a certain word as spam. The system is able to figure out those common words, the occurrences.
Yeah, I think, so spam is an interesting case because presumably spammers are getting more sophisticated. And so the spam filters that might have worked 5 years ago probably wouldn't work that well right now. So that is another aspect of machine learning that's pretty important, is that very often it's pretty rare to have a problem that you solve once and for all with machine learning. Usually you want to go back and revisit it periodically and see if the solutions you came up with last year or last month are still applying. So spam is a good example of, I don't know if people talk about Nigerian princes anymore because that's just such a cliche at this point, but the basic formula of we're going to pretend that there's some amount of money that's sitting in an account somewhere and you just have to send us some small deposit and we'll release it to you. The exact details of that might change, and so then you have to keep retraining your machine learning algorithm to sort of continue to make good decisions in that scenario.
And two of the things that you mentioned of characteristics of an email is the first one was the words, certain words that occur, and the other one is the domain. How is this information represented? Is there a specific format for this?
Oh, yeah,
for the machine learning model?
Yeah, that's a really good question, and it's very important. So in this particular case, usually with something like text classification, the simplest thing that you can do is you can treat each word as its own type of feature. So a lot of these machine learning algorithms under the hood, they assume that there's big matrices of attributes. So imagine a matrix is kind of a big data table, and each row in that table is an email in this case, and each column in that matrix is a word. And so if there's a particular word that shows up in a particular email, then you'll get probably a 1 in that spot in the matrix, and if it doesn't show up, then there's a 0. So then with this big matrix, which is going to be mostly zeros. We'll call it, it's often called a sparse matrix because it's mostly zeros. There's very few ones. With that matrix representation, then you can put that into, some of your standard machine learning algorithms, and it can figure out then how to find the structure in that matrix that allows it to understand which words are most closely associated with the emails that you've classified as spam.
So you mentioned the sparse matrix. Is there an impact in the fact that there are a lot of zeros in this data structure?
Oh, that's a really good question. And in general, yes. So some algorithms, depending on exactly what type of algorithm you're using, that can be no problem at all, or it can be a big concern. And so one of the other important aspects of machine learning is sometimes thinking about different representations of your data. So the way that I described it is just the simplest way that you might represent the data in an email, but there's other algorithms that can be a little bit more compressed with respect to how it, represents the types of words or the types of sentences that are showing up in an email. And so those types of decisions about how you're going to represent your data have a pretty intimate connection with the type of algorithm that you're actually going to use to do the pattern recognition, so to speak, the actual supervised classification algorithm. And so, yeah, it makes a huge difference. And this is a place where people spend a lot of time and effort is thinking about the best ways to represent their data. Because this gets back very quickly to the idea of that the data is representing some kind of latent truth that we're trying to understand. And so then the way that the data is formatted can make it very easy for us to find that truth, so to speak, or it can make it, really hard. So it's worth thinking about pretty carefully.
And what is one way in which this data has been compressed in other data structures?
Oh, sure. So one that I think is pretty interesting is you brought up the issue at the very beginning of Netflix movie recommendations. And that's another case of where you have a big sparse matrix. So you imagine that each person who watches movies is a row, and each possible movie that they could watch is a column. And so most people will only watch 1% of movies or something like that, of all the movies that are out there. And most movies that are out there are not going to be watched by even a significant fraction of all the Netflix users. So you have, again, this kind of big sparse matrix. And so what you can do with something like Netflix is you can use what's called matrix factorization. And the rough idea of matrix factorization is instead of having this big sparse matrix, let's imagine that there's basically two factors or two different types of attributes that we're trying to understand. We're trying to understand types of users who watch movies. We say that there's certain buckets of users or segments of users. There's, let's say, families with kids, and those watch certain types of movies. And then there might also be 20-year-old guys who really like other types of movies. And then maybe there's middle-aged women who like a third type of movie. Or not even just a single type of movie, but certain admixtures of movies. So we have kind of types of users on the one hand, and then we have analogously types of movies on the other hand. So you might have action movies or mysteries or foreign documentaries or whatever. And so whether a particular user likes a particular movie is kind of a combination of what type of user they are and what type of movie it is. And so that's a way, there's sort of this linear algebra process that you can go through to try to take this big sparse matrix and approximate it as basically the product of two smaller matrices, one that's about your users and one that's about your movies. And so that's a way of representing that same data in a different way, but in a way that can sometimes make it a lot more easy and direct to try to figure out, in this case, if a particular user is going to like a particular type of movie.
Yeah, and this is also good, I think, because it reminds me of what we talked about earlier about updating a model. What you start watching as a little kid, and then suddenly you're a teenager, then you're married, and your interests keep evolving. And with this way, it would be updating it, right? Because there's different matrices.
Yeah, and one of the other things that's nice about it is in recommendation engines, there's also this classic problem of cold starts. So let's say there's a new movie that gets added to Netflix next month, and Netflix is trying to figure out if they should give it really valuable real estate on the front page and like advertise it to people. So they're basically trying to figure out if a lot of people are going to want to watch it. But they have no data on this movie yet. They don't know who's watched it or who would like it before, or who. They don't have any information about who has watched it yet because they haven't put it on their website. And so this is kind of a tricky place to be in terms of machine learning, because usually machine learning is about pattern recognition and there's no pattern there yet. But if you have some other contextual information, like we know that this is an action movie, then you have a little bit of a better place where you're starting from, and you have some idea of who are the people who like action movies. And so that's a place where you can be a little bit more effective, especially right at the beginning, and then sort of refine those estimates as you actually put the movie out there and you collect more data about who's watching it.
And we've been talking about supervised machine learning earlier, about classification, the spam email, putting the data into buckets, spam or not spam. Can supervised learning be applied also to values that are continuous instead of discrete?
Oh, sure. Yeah. So that's usually called regression. And actually, a lot of the same algorithms can be used for classification and regression. And it's kind of an issue of just flipping back and forth between the final type of output that you want. So definitely, yeah.
Mm-hmm. What is one example of what you just mentioned, that the algorithms can be applied to both?
Oh, so decision trees are one type of algorithm that I know that there's decision tree regression and there's decision tree classification.
Okay. Can you explain a little bit more regression, for example, linear regression, what the objective is?
Oh, sure. Yeah. So linear regression, like you said, has more of a continuous output. And maybe the way to think about this that's a little bit more useful is where classification is trying to figure out if something is A or B, spam or not spam. The thing about spam and not spam is there isn't really a natural ordering of those two things. Like you wouldn't say that spam has an inherently like higher value than not spam or vice versa. But if you're trying to do something like predict somebody's income based off of like other attributes that you can see about them, then obviously there's a natural ordering. If you have one person that you predict that they make $10,000 a year and there's someone else who makes $100,000 a year, there's a sort of a natural ordering to them. And regardless of what amount of money somebody makes, you can put them in this kind of spectrum that has this natural ordering to it. So what linear regression tries to do is it says we have a list of attributes about a certain person and we're trying to predict their income. We'll just use that example for now. So based on these attributes, what do I see as the relationship between a person's attribute and their income? So one example might be age, and you might say that the older someone tends to get, up to a certain point at least, the more money they tend to make because they're more experienced or whatever. You might also say something like, I can observe what kind of car this person drives, and I know that there's certain patterns in terms of income versus the type of transportation that you use. Basically, that richer people have access to nicer cars. And none of these patterns are going to hold absolutely for every single case that you can look at, but statistically, they'll usually hold, and from that you can make, sort of predictions. The quality of those predictions will depend very much on how good your data is, and to a lesser extent, how good your algorithm is. But again, you're getting a little bit closer than if you were to just sort of make a shot in the dark guess. And
a way to visualize this is if we plot, for example, in one axis the income, and in another axis the type of car, then not the type of car, but the price of the car, to maybe predict with what income how much you spend in cars, right?
Yeah, that would give you some idea. And then you could imagine fitting like a line to basically that distribution that you see. And the slope of that line is going to tell you sort of how much more you're going to estimate about somebody's income once you know how expensive their car is.
How do we measure how good the line is compared to the data?
Yeah, so there's a few standard metrics that, kind of everyone uses. So for something like comparing lines to a data set, what you'll very often use is for every data point that you have in your data set, you'll pick the prediction that's given to you by the line. Like if someone, driving a car of this value, or if I see someone driving a car that has a certain value, what do I predict about their income, and that's going to be just where do they fall on this line. And then you'll say for that person, what was their actual income? And so let's say there's somebody who's driving a really expensive car, and so I think they make $100,000 a year. And then when I actually look at my data set, I find that they make $110,000 a year. So that difference, that $10,000, then usually I'll say that was my error, or sometimes you square it for other reasons that we don't have to get into. And then you sum that up over your whole data set, and you say, and probably divide by the number of points that you had, and you said, this is a metric for my goodness of fit of this line. But I think one of the other things that's interesting about metrics is that for a lot of machine learning algorithms, there's standard metrics that you can use. So for classification, you can use something like accuracy, which is how many did you get right divided by how many total cases did you try to classify. But one of the big challenges of machine learning in data science is trying to figure out if those metrics are like really actually measuring the thing that you care about, because usually they aren't, and you have to be a little bit smarter than just the metrics and figure out exactly what it is you care about and then modify the metrics a little bit to reflect that. So you usually have good options, but then part of the artistry is like knowing when to leave those options behind.
And we'll talk a little bit more about evaluation metrics later on. But first, I want to shift the topic a little bit to unsupervised machine learning. We've been talking about supervised machine learning for discrete values and for continuous values. How is unsupervised machine learning different than supervised?
So the sort of canonical answer is that for in supervised machine learning, you have correct answers that sort of came to you with your data set. With unsupervised machine learning, you don't have that luxury. You just have data. And so usually the types of questions that you can ask of that data are kind of different and very often constrained by the fact that there's no sort of like correct answer that you're trying to find. And so that really changes the character of the work in a lot of ways, in my opinion, when I've tried to do unsupervised learning. It's very challenging, and it's a really different way of thinking about your data, because with supervised machine learning, there's basically like a correct answer. And what you want to do is just try to get as close as possible to that correct answer. With unsupervised machine learning, it can be very tricky to try to understand what a good answer looks like so that you would recognize it when you saw it. Unsupervised methods would be things like clustering. If you have a data set and you think there's kind of like groups or clumps or clusters in that data, then clustering is usually considered an unsupervised method. And also some of these matrix decomposition or some of the feature reduction techniques like principal components analysis is another, if people are familiar with that, is another unsupervised method. So again, there's sort of different types of questions that you might try to answer with unsupervised learning, and it, in my experience, is really, really hard.
What do some of those questions look like that you've done in the past?
Yeah, so the biggest one in my experience that I've worked with before has been clustering. And again, that's just sort of the idea that you have, these blobs in the data and you want to try to find them, that there's sort of these coherent clumps. And that's hard because with a lot of real world data sets, you don't know if there are clusters in the data set to begin with. So if you don't find any, it's really hard to know if that's because you're doing a bad job or because it just doesn't exist. This gets back a little bit to the idea of like truth and like, what are we trying to understand here in the world? And then for things like principal components analysis, the idea of principal components analysis is you're trying to find sort of like directions in your data set in a lower dimensional space. Again, this gets back to the idea of like feature representation sometimes. Directions in your data set in a lower dimensional space that maximize the variance in your data. So you're trying to find ways of sort of compressing the data down to the aspects that make it like the most variable. That's not a particularly good way of explaining it. But the point is that it's something that you can do without knowing any sort of quote unquote correct answers for your data. So that can be like pretty useful when you don't have labels to rely on.
And where would we see this on a regular basis? For example, for supervised, we talked about the spam email. Unsupervised machine learning, is it widely used? Is there any systems that we interact with that under the hood might be using unsupervised machine learning?
Oh, yeah, that's a good question. So a lot of clustering analyses, and so this will sometimes show up in something like maybe if you work in marketing, trying to think of segmentation. So if you think that your users might fall into a few main buckets, let's say I'm thinking of selling a computer and I have my power users like my programmers and my data scientists and whatever, but then I also have people who just use it as like an internet machine and they just watch movies on it and use Facebook. Maybe there's people who use it as a work machine, but they're not programming on it, you know. So you could think that maybe there's a data set that would somehow allow you to pick out that there's these distinct groups. Some of the other interesting places for unsupervised methods are off the top of my head. I think there's some really cool stuff that I've heard about in genomics. So genomics, they have this problem where there's something like 3 billion base pairs in the human genome. And so trying to figure out which of those are actual genes that control, you know, things that we might care about, like diseases or, you know, whether you get sick eventually, whether you have health problems of all different kinds. And so that can be a really challenging machine learning problem for a lot of reasons. And so sometimes you have to throw unsupervised methods at that because it's not well defined enough at the outset what question it is you're trying to answer. And so just trying to like bring that data problem under control a little bit sometimes forces you into a space that's a little bit more unsupervised.
So unsupervised might also be more about discoverability because you don't necessarily know what you're looking for.
Yeah, I think that's probably fair. You know, supervised methods are what you use when you know what it is you're trying to answer. And then unsupervised methods are for either where you don't have that labeled data available or where you don't exactly know how to slice and dice the data yet.
We've mentioned several algorithms for supervised and unsupervised machine learning. We also talked about some potential applications of it. In what language are machine learning algorithms typically written in?
The go-to languages, if you're in data science anyway, are R and Python. And then I think there's also implementations that are in a number of other languages that just don't have as much pickup in the community. So C++ or Java or whatever. There's, you know, machine learning implementations in a lot of other languages that, you know, are sometimes used in like boutique cases. But I think R and Python are like the powerhouse languages.
So Python is the most popular one?
I think so. I think it depends a little bit on how you define data scientist or machine learning. But I think R and Python are fairly close. I like Python better, but that's just me. Okay.
Let's talk about the data in machine learning. Before choosing a machine learning algorithm, I've heard that it's important to look at the data first. Do you agree with this?
Yes, I think that's incredibly important. I think it's also incredibly hard sometimes. So I'll just say that at the outset. But things like missing data, things like biases in your data, things like mistakes and outliers and things like that, those can really mess up a machine learning algorithm. And the fastest way to get a handle on a data set is just by looking at it.
And for example, if you're inspecting a large data set, you would just pick a subset of it, right? Randomly or?
Yeah, I guess it depends on how big. I mean, if you can look at the whole data set, then, you know, by all means, look at the whole thing. But yeah, if you're working with big enough data sets, you'll probably have to like randomly subset it.
Okay. Another common term when talking about data and machine learning is cleaning the data and transforming the data.
Yeah.
What does this mean? What does this encompass?
Oh, that is an excellent question. And I will name some things, but invariably, you know, there's always corner cases that don't get covered by the stuff that you think you need to do. So a few examples are looking for outliers. So data points that are just far, far outside of the general distribution. And this can either be because they're truly interesting and anomalous events, like you managed to just find Bill Gates in your data set or something, and Bill Gates just is a very different person than the rest of the world in a lot of ways. Or what's more likely is that there's a mistake in the data and that somebody, you know, hit an extra 9 when they were entering somebody's income, and it's just an error. So those are things that you would then want to clean up. Very often you can also have missing data, and so then you have to figure out what you want to do in those cases. Most machine learning algorithms don't particularly handle it well if you have missing data. There's all kinds of things you can do to deal with that'll have different implications downstream for the answers that you get. Yeah, I think that it's really hard to know in advance what kind of shape data is going to be in and how much work it's going to be to clean it. Like, it's one of those things that you really only start to know how messy a data set is once you get your hands on it. But it's hugely important. Yeah, that's a really good point. And it's something that I would say most, I mean, the other thing is, I'm even getting ahead of myself here. A lot of times data doesn't come in like a nice matrix format where you have, rows and columns. It comes in some mess, and you have to figure out how to format it before you can even start to think about visualizing it. And, maybe there's a whole bunch of tables that you need to join together, and it's all complicated that way too. So yeah, it can actually end up being a huge part of your work as a data scientist, which is kind of too bad because it's not particularly fun. But whoever figures out a good way to reliably automate this is going to make $1 billion, and more power to them, because our lives are all going to be, our lives in the machine learning and data science community anyway, we'll all benefit from it.
Yeah. Do current tools, for example, Python, alleviate some of this, for example, in finding outliers?
Yeah. There's certainly methods that you can bring to bear on this. The thing that's hard is just knowing what kind of messy data problem you have and how to fix it. So a lot of problems are, as soon as you figure out the right way to like slice and dice the data that you can see it, it's immediately obvious what the problem is. It's just that usually figuring out how to slice and dice the data to understand what's going on, that's the hard part, is just figuring out what your problem is.
I wonder if machine learning can be applied to that, like to all the cleaning before and after data sets.
Personally, deeply hope so. Like, I think that there's stuff that you can, the thing that's tricky about it is I think you can get probably 80% of the way there with a lot of tools that are already on the market. It's just like knowing how to put them together for a particular data set. And the thing about it is that even if you get 80% of the way there, that last 20% can still really mess you up. So I think a lot of data science, as much as we would love to have automated cleaning tools, I think there would also be a lot of skepticism of them in the data science community. I think data scientists would still, I would still tell people to look at their data, make sure you understand it, even if you have the best cleaning tool in the world. I don't think there's such a thing as a perfect cleaning tool.
One more thing related to data is for supervised algorithms, like we discussed earlier, we provide label data. When building the machine learning model, what does it mean, the training data and the testing data?
Oh, sure. Yeah, this is a really good point. So the idea is you have some big data set that you are starting with. So when we say training a machine learning algorithm, it's basically giving it a set of labeled examples and having it use those to figure out what the patterns are. But the thing about it is that then the next question you want to ask is, how good is this algorithm that I've just made? How good is it going to be at predicting labels for new cases that it hasn't seen yet? And the way you need to answer that question is you need to give it new cases that it hasn't seen yet, but for which you actually know the correct answer, so you can see if it gets it right or not. And so that's what your test data set is for. And it's really important that you separate your training data from your test data before you start doing any machine learning, because it's really easy for machine learning algorithms to basically just memorize their training data, which is not a particularly good position to be in, because it means that all they know is what they've memorized. They haven't figured out how to like extend it to new cases. And then the other problem is that then if you give it an example that it's already seen before and you say, do you know the answer to this? Then it will tell you, yes, of course, it'll give you the right answer, but that doesn't necessarily mean that it would get the right answer in a similar case in the future. Like, again, it's sort of this problem where it's just memorized the answer. It hasn't really like learned anything. So it's really important that you not be fooled by that particular mistake. And that's what your test data is for, that you have to keep it partitioned off from your training data, and you only use it to try to understand the performance of your algorithm on new cases that it hasn't seen before.
What is the process for determining what percentage of the data we should use for training and what percentage for testing?
Yeah, different people will give you different answers for this, and it can depend on sort of how much data you have overall and like how high the dimensionality is and stuff like that. One of the things that is a little bit nicer than just training and testing, as I described it now, is what's called KFold Crossvalidation, or sometimes it's called Nfold Crossvalidation. And so the idea is, imagine you have your data set, and let's say it's a threefold cross-validation that you're running. So in that case, what you'll do is you'll split your data into 3 equal parts just randomly. You train on 2/3, and then you test on the third piece. And then you do that again, but you train on, instead of train on A and B and test on C, you train on B and C and you test on A. And so then you can do that, 3 times in total. And so then every example that you have ends up being used for both training and testing. So it's a way that you can get like a little bit more juice out of your data. So that's actually probably the preferred way to do evaluation, is actually using KFold cross-validation.
And it's also important that the data is randomized, right?
Yes, that's hugely important. There are so many times that I've gotten very confused by having a data set that isn't randomized. So by not randomized, I mean, like, imagine our spam case, but all of our spam emails are like in the first, 100 rows, and then everything after that is not spam. It's really easy to get an algorithm that doesn't do very well, because you're basically training it on one type of data and then testing it on another type of data. And of course it wouldn't do well. Why would it know what not spam looks like? It only knows what spam looks like. So if you randomize your data at the outset, then it should solve this problem. But it's just one of those like classic things that every time I do it, I get very confused for about a half hour. And then hopefully less at this point. I'm a little bit smarter, but it used to be I would be just scratching my head for 45 minutes trying to figure out what was going on. And then you figure it out and you kind of just smack yourself on the head, and then it's really easy to fix. But it's very confusing when that happens to you.
Yeah. Do you randomize it using Python?
So in Python, what I'm usually using for machine learning is scikit-learn, which is just a library for machine learning. And then in the scikit-learn KFold cross-validation, and also in all of their cross-validation stuff, I think they have randomization flags that you can set that'll just like shuffle everything. So I don't have to do it manually anymore, although that was what I used to do. Yeah.
Yeah. Yeah, because that's what I was wondering. I'm like, it should just be a requirement, but a flag makes sense.
Yeah, I think it's a flag at this point.
Yes. Let's talk now a little bit more on evaluation metrics. You mentioned earlier accuracy, and that you don't always want to go by the accuracy. Why is that? Why is accuracy not sufficient?
Yeah, it's a really good question. There are a few different answers that I might give. So just a couple off the top of my head. One is, imagine that you have a data set that's very imbalanced. So let's suppose that the vast majority of the email that you get is actually legitimate email, and there's only, let's say, 10% of it is spam. And so then if what you're doing is, it's really easy in those circumstances for machine learning algorithms to, the heuristic that they learn is just always classify it as not spam. And so it's not, your machine learning algorithm isn't really actually doing anything in that case. But if you're relying on accuracy to tell you if you have a good algorithm or not, then it's going to say, even though your algorithm basically isn't doing anything, it's still getting it right 90% of the time. And so then that 90% accuracy metric might fool you into thinking that you have a really great classifier when you have, you're very far from that. Another thing about accuracy is that it treats all kinds of errors and all kinds of successes as like basically equal. So let's imagine that what we have is some kind of classifier that's trying to tell if you have a very serious disease. And let's suppose that this disease is, if you catch it early, then treatment is like fairly straightforward and things like that. But if you don't catch it, then it can be like a gigantic problem. And so maybe in that case, it's more expensive for you to make the mistake of missing a case of this disease than it is for you to like accidentally flag someone as having it and asking them to come in for more testing. Because let's say the further testing would just verify that they were actually okay and they didn't need to do anything. So there's kind of different costs that are associated with the different types of mistakes you might make. Accuracy by itself won't reflect that. And so you might end up in this case where, you think that it's equally harmful to like make both of those kinds of mistakes, but in real life, that might not be the case.
And what you mean in the medical example is that you don't want to ignore people that were detected to have the disease, but they turn out to not have it. You want to evaluate whoever turned positive, right?
Yeah, so in that case, I guess what I'm imagining is that it's not that expensive for us to accidentally have a false positive, to accidentally think that someone has this disease when they don't. Like, let's say that the treatment is they have to take extra vitamins. And so maybe that's not that big of a deal. If you don't have the disease, like taking extra vitamins, you have to pay a little bit of money, and that might not be great, but like it's not a big problem. But if you're one of the people who actually did have the disease, you don't get diagnosed, and so you're not able to take the vitamins, and so you might get really sick, and that's actually a huge problem. So in this case, we would probably want to err on the side of, overdiagnosing a little bit in this particular case, that even if we aren't exactly sure, if we think there's like even a kind of slight chance that someone might have this disease, like just go ahead and prescribe the vitamins. Like that's the kind of mistake that we would prefer to make. And so accuracy is going to treat both of those kinds of mistakes as equally bad when in fact they're not.
What is the name of this other metric for evaluating? One is accuracy, but how do you call the one where you're also considering false positives?
Oh yeah, so there's a few different ones depending on exactly what parts of it you care about the most. So there's precision, and that's the idea of, for people who I flag as having this disease, how often am I actually correct about it? There's recall, which says that of everyone who gets tested, how often do I actually detect it when somebody has the disease? And then there's different admixtures. So there's what's called the receiver operator characteristic curve, which is a little bit more sophisticated. And so that's trying to look at like both the true positive rate and the false positive rate at the same time. There's what's called the F score, which is a combination of precision and recall. And then if you can do it, the thing that's best is to attach types of costs to each of the mistakes that you might make. And this might be really hard for most cases, but let's say that you have an easier example of like you're trying to sell products and you're just figuring out who to market products to. Like you probably know approximately how expensive it is to like advertise to one more person. You probably know how much money you expect to make if you manage to successfully advertise to them and they buy your product. So then what you're trying to do is just do this sort of like cost benefit trade-off, and you're going to pick the point that just maximizes how much money you make. So that's going to be some combination of how much money you make because people are buying your product, and then there's going to be the money that you lose because you have to advertise to people, and that costs money. And so just finding like kind of the maximum on that curve is probably what you want to do.
And like you said, choosing an evaluation metric can depend on the type of problem that we're dealing with, right? Medical is not necessarily the same, as you said, marketing.
Yeah, for sure. And like, are you trying to do classification of just people into, different buckets? Or one of the things that comes up in medicine a lot is you're trying to assess the risk of something happening to a person within, let's say the risk of them getting heart disease in the next 5 years or something like that. And so that getting that risk score correct, having that be an accurate probability basically of what the actual risk is for them, that's a slightly different question, and you're going to use slightly different metrics to figure out if your model is doing a good job, if that's what you want out is an accurate probability instead of like an accurate label. So there's all kinds of different scenarios depending on exactly what it is you're studying and what it is you're trying to measure.
Last question. I want to talk about machine learning as a career or data science. What does someone that work in this field do on a regular basis at a higher level?
So yeah, a lot of it is the cleaning, actually, the data cleaning. I hate to say it, but it's true. Yep. And that's really important because like the quality of your data has a huge impact on how good you are at your job, like that just propagates all the way downstream. So a lot of my time is also spent thinking about whether the data that I have is appropriate for the questions that I'm trying to answer with it, whether like the representation I've picked is a good one, trying out new features, that sort of thing. You can spend a lot of time that way. And then it depends a little bit on the case, but for some data scientists, it's a lot of figuring out just sort of one-off answers to questions. And so that might be sort of feel a little bit more exploratory, and you're working in like a notebook and it's a new question every day. For other data scientists, they're more like software engineers. So once you figure out how to solve a problem, your task is figuring out how to solve it, repeatedly at very high scale. you need to make sure that the results that you're getting are understandable by people who aren't technical. And so that can be a lot of work as well, is like figuring out how to approach it as a software engineering problem in addition to a statistics problem.
Do you sometimes go beyond the data that you have stored in your computer and take into account events that are happening in the news or information that you can gather from somewhere else?
Oh, that's an interesting question. I mean, so I'm always paying attention. So the type of work that I do in particular for data science deals with a lot of like person level data. And so thinking about what's going on in the world and how people are interacting with technology and, you know, how they might be responding to events in the world, like that can be pretty important. So yeah, thinking about if we want to set up a way to get some data from Twitter, for example, might be a way that I spend some time. Yeah, and I think a lot of the work is also because this is a field that's changing so quickly, and there's a new thing coming out every day. A lot of my job is also, as much as possible, trying to keep up with that fire hose and make sure, you know, there's no way you can learn everything, but trying to make sure that at least you know kind of where the field is heading and making sure that you don't get too far behind.
What do you use to keep yourself up to date? What are some of the resources now that you brought it up? Do you have anything other than Udacity, of course?
Yeah, sure. Well, I have my own podcast, so I'm a fan of that. So,
what's your podcast?
It's called Linear Digressions. I talk about machine learning for 20 minutes every week.
That's awesome.
Yeah,
I'll include this in the show notes.
And that's actually, I mean, this doesn't generalize that well to like, you know, you have to have a podcast to do this, so it, you know, that takes a lot of work. But that's actually been, for me personally, the way that I've learned a ton, because every week I have to come up with something to talk about, and that really forces you to stop and think about, you know, you're like, oh no, what am I going to talk about this week? And I think also participating in like the larger data science community. So for some people, this might mean using Twitter and following data scientists on Twitter. Sometimes this means, you know, if you are fortunate enough to work in a company where you have a lot of colleagues who are really paying attention to this stuff, using them as resources, participating in the open source community. I find that there's a lot of noise around data science and machine learning. And so trying to figure out, it's not that hard to find people talking about this. It can be harder to find really good, high quality sources. So whenever you find sort of like smart people who are talking about it and trying to understand it, that can be a really good place to kind of plant your flag and listen in on those conversations and contribute to them too. So that can take a lot of forms, but you know, just trying to find those little pockets of the community where good work is being done and following along has been really beneficial to me.
Katie, thank you for coming on the show. It was great talking to you today.
Oh, it was absolutely my pleasure. Thank you for such wonderful conversation.
For Software Engineering Radio, this was Edaena Salinas. Thank you for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more information about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can write comments on each episode on the website or write a review on iTunes. Mention or message us on Twitter at SE Radio, or search for the Software Engineering Radio Group on LinkedIn, Google+, or Facebook. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under the Creative Commons 2.5 license. Thanks again for your support.